Hey everyone, welcome to this week's discussion video on probabilities and Bayes nets. Let's get started. So starting off on probability, I'm sure all of you guys have seen probabilities before, but let's just kind of recap quickly the things that you'll need to know for this class. So first of all, here are kind of the three basic probability types that we're going to be dealing with. So we have the singular probability of x, we have the conditional probability of x given y, and then we have the joint probability of x and y. And a lot of what we're going to be talking about with probabilities are going to be formulas on how we go from one table to another. So let's jump into the first formula right now, which is going to be the formula to go from the joint probability of x and y into the singular probability of x. And we're going to use this equation that we've listed right here. So basically the probability of x is going to be equal to the sum over y's of the probability of x comma y. So let's go through the quick calculation to calculate probability of plus x. Well, that's going to be the sum over these two rows, the probability of plus x and plus y, and the probability of plus x and minus y. Okay, so we're just going to sum up over these two entries, so 0.2 plus 0.3, and that's going to give us 0.5. Right? Doing the same thing with minus x, we get the sum over these two rows, which is also 0.5. And then for the probability of y, well, the first one is going to be the sum for plus y. It's going to be the sum over the two rows that have entries plus y. So that's row number 1 and row number 3. And that gives us 0.6. And then for minus y, it's going to be row number 2 and row number 4. It's going to give us 0.4. And to verify that your calculations are correct, well, probability of x and probability of y, they're just normalized probability tables. So the entries should all sum to 1. And we see that this is the case here. So that's just a quick sanity check for your calculations. Okay, so that's going to be the first equation to go to the singular probability table from a joint. The next equation that we're going to talk about is to go from a joint probability of x comma y to a conditional probability of x given y. And to do that, we use this equation down here. So the probability of x given y is going to be equal to the probability of x comma y divided by the probability of y. And just rewriting that in terms of our first equation, it's going to be the probability of x comma y divided by the sum over x's of the probability of x comma y. So recall that this bottom portion here, the sum over x's of the probability of x comma y, this is just equal to the probability of y. Alright, so let's go over the first one as an example. So the probability of plus x given plus y. Well, on the top we'll have probability of plus x comma plus y, so probability of plus x and plus y. And on the bottom we'll have the probability of plus y, which is the probability of plus x comma plus y plus the probability of minus x comma plus y. And so that's going to give us 0.2 on top and 0.2 plus 0.4 on the bottom, which is going to give us 1/3. Going through the rest of these examples, the probability of plus x given minus y is going to be the probability of plus x and minus y, so row 2, divided by the probability of minus y, which is the sum of row 2 and row 4. It's going to give us 3/4. Probability of minus x given plus y is going to be row number 3 divided by the sum of row number 1 and row number 3, which gives us 2/3, and the final one is going to be 1/4. So this is the second equation to keep in mind with probabilities, and it gives us the conditional from the joint and the singular. So let's move on to the third equation, which is going to give us the joint from the singular and the conditional. So the equation is going to look like this. The probability of x and y is going to be equal to the probability of x times the probability of y given x. If you're really paying attention, you'll see that this is just another way to rewrite the second equation here, where basically all we do is we move y to the left-hand side. We get the joint probability is equal to the singular times the conditional, which is exactly what we have here. But let's just go through an example of this. So say we're given the probability of the weather and the probability of the dryness given the weather. So if we wanted to calculate the probability of wet and sun, what we would do is we would take the probability of sun times the probability of wet given sun. So that's 0.8 times 0.1, which is going to give us 0.08. For P of dry and sun, we have the probability of sun times the probability of dry given sun, which is 0.8 times 0.9, or 0.72. Wet and rain, we get the probability of rain times the probability of wet given rain, which is 0.14. And then for dry and rain, we'll just multiply the probability of rain times the probability of dry given rain, which is 0.06. Okay, so that's our third equation, and it's going to give us the joint based on the singular and the conditional. Now, this equation is what we're going to call the product rule. We can also expand this rule into what we'll call the chain rule, which is going to tell us the joint probability of a bunch of events x sub 1 to x sub n. And this chain rule is just going to be a generalization of this product rule. So it says the probability of the joint of all these events x1 to xn is equal to the product of I from 1 to n of the probability of x sub I given x sub 1 all the way to x sub I minus 1. So what that's going to look like is it's going to be like the probability of x sub 1 times the probability of x sub 2 given x sub 1 times the probability of x sub 3 given x sub 1 and x sub 2, and so on. And this we'll call the chain rule. Okay, on to one last very important concept in probability. With this product rule equation, notice that we can write the probability of x comma y in two different ways, right? It can be written as the probability of x times the probability of y given x, which is what we have here. But it can also be written as the probability of x given y times the probability of y. Okay? And these two are functionally equivalent, right? So if we look at this quantity in the middle and this quantity on the right, well, we can get a new rule, which is something that's written like this. So here all we've done is we've divided p of y from both sides. And so this shows us that we can get the probability of x given y from the table p of y given x. And so this is a very important concept, and this is called Bayes' rule. Okay, so that's just about all I wanted to talk about on probability. With that, let's start talking about Bayes nets and independence. So for two variables, x and y, we'll say that they're independent if the probability of x comma y is equal to the probability of x times the probability of y. Okay, so recall that if we were writing this quantity with the chain rule, this probability of x comma y quantity, it would be equal to the probability of x times the probability of y given x. Okay, so that's just this guy here. Well, basically when we have independence, we can simplify this probability of y given x term, or x given y term, into just probability of x. Okay, so independence basically lets us simplify our probability table by rewriting this right here. By rewriting probability of x given y as just probability of x. Basically what independence says is that the distribution of x is not affected by the random variable y. Okay, so the probability of x given y is just going to be the same thing as the probability of x. We can also have conditional independence, which says that two variables x and y are independent given some variable z. And basically the equations are going to look the same as just regular independence, except there's going to be a conditioning on z in every probability table. Okay, so what do Bayes nets do? A Bayes net is just going to be a directed graph where each node represents some conditional probability table. So CPT stands for conditional probability table. And what that conditional probability table for the node is going to be is the variable for the node given the parents. Okay, so let's look at some of these nodes. So for example, the node for j is going to be the probability of j given the parents of j, which is a, so the probability of j given a. The conditional probability table for node a is going to be the probability of a given the parents of a, which is b and e. so probability of A given B and E. And the probability table for node E is just going to be P of E because E has no parents. Okay, and so what all of these tables are going to encode is a list of conditional independencies, right? So each node is dependent on its parents and affects the nodes below it. So with these conditional probability tables, we can simplify the probability of some x of I given all these variables x1 to xi minus 1 as just the probability of x of I given its parents in the base net. And that means, if you recall the chain rule, to get the joint probability table of a bunch of events x of I to x of n, instead of writing this term as the probability of x of I given x sub 1 to x of I minus 1, we can instead write it as the probability of x of I given the parents of x of I in the Bayes net. And so this simplifies our calculations. Okay, so that's all for this week on probability and Bayes nets. We will get into more on Bayes nets next week when we talk about how to do inference on Bayes nets and things like that. But I hope this helps, and good luck on your homework. See you guys next week.